In this video, we're going to take a look at properties of the rectangle, rhombus, and square. So to start off with, here's a review of the properties for a parallelogram. And I'm going to take a look at this quadrilateral chart. We're going to investigate the rectangle, rhombus, and square, and they belong within the parallelograms. So that means my rectangle. I'm going to draw a picture to demonstrate its definition. It's a four-sided figure, not drawn to scale, but it has four right angles. That's its definition. Since a rectangle is a parallelogram, that means the four properties of a parallelogram also apply to all rectangles. There is one property that's unique to all rectangles. The diagonals are congruent to each other. So if I take a look at this example, ABCD is a rectangle. I gave two side lengths, one's 3 and one's 4. According to my new property, the diagonal lines are congruent to each other. So what I'm going to do is try to find this diagonal line. I'm just going to look at ACD. Since this is a rectangle to start with, my angle D is actually a right angle. That means I have a right triangle. I can apply the Pythagorean theorem to try to find the length from A to C. So that means 3 squared plus 4 squared would equal the segment AC squared. So my diagonal line, AC squared, would equal 25. If I apply the square root to that, that means the length from AC should equal the number 5. Now that I have this new property about rectangles, AC would equal 5, but BD would also equal the number 5. And just to review about properties from parallelograms, my diagonals bisect each other. But since it's a rectangle and the diagonal lines are the same length, all four of these segments are actually going to be the same length. So if A to C is 5, that means each of these individual pieces would be 2.5 in length. All four of those segments would be the same length. We're going to use our properties to try to find all missing angles in this rectangle. Being that it's a rectangle, we know that these are 90-degree angles in each corner. That means this missing angle, angle NKM, should be 70 degrees because those two need to add up to 90 degrees. Being that it's also a parallelogram, I have alternate interior angles. But now that we know that the diagonal lines are congruent to each other, and they also bisect each other, I'm going to put some markings in here. If you notice, all four individual triangles will be isosceles. So now I can find these other angles. This one should also be 20 degrees because it's a base angle. This one should also be 70. Now if I want to use my triangle sum, I can find my angles that are at point O. So that's how I can find every single angle in a rectangle if I was only given one to start with. Okay, the next shape we're going to look at is the rhombus. So just as a review, a rhombus, not drawn to scale, but based on the markings, this is the definition of a rhombus. A quadrilateral that has four congruent sides. Since the rhombus is also a parallelogram, that means it has the same four properties that all parallelograms do. There are two more unique properties for the rhombi. and we're going to look at these properties in the next example. My top example, it is a rhombus, and I gave one angle that's 20 degrees. One of my unique properties for a rhombus is that the diagonal lines are perpendicular to each other. That means I have four 90-degree angles right here within the center of that rhombus. Now I'm going to take a look at triangle HOE. It's a right triangle, so I can find my missing angle is 70. Another property for the rhombus is that the diagonal lines are angle bisectors. That means this angle of my original rhombus is being bisected by segment HF. Each of these angles would be 20 degrees apiece. Once again, I'm going to apply my right triangle, so that gives me a couple more angles I can find. In a parallelogram, opposite angles are always congruent. So my original angle H should be the exact same as my original angle F. And being that the diagonal lines bisect that angle, that makes each one of these 20 degrees apiece. And my last two missing angles would each be 70. In the example below, I gave the length of two segments. So this segment has a measurement of 3, which means because it's a parallelogram and diagonal lines are bisected, segment OA is also a 3. My full segment D to B equals 8. That means just from D to O is 4 and O to B is 4. I can find what the sides are around the original rhombus. I'm going to use that property that the diagonal lines are perpendicular. So I'm actually dealing with right triangles. If I were to use the Pythagorean theorem, I could find out one of the sides to the rhombus. In this example, I'll just use CB. And these numbers were used before, so I'm just going to kind of skip ahead to this part. That means the length of CB should equal the value 5. Because it's a rhombus and all four sides are the same, each of those sides would each be a 5. And then the last shape we're going to look at is a square. So the definition of a square, four-sided figure, it has 4 right angles as well as 4 sides that are congruent. Since a square is a parallelogram, it takes on all the properties of a parallelogram. Since a square is also a rectangle as well as a rhombus, it takes on the other properties we just discussed about the rectangle and rhombus. So there are 7 additional properties that all squares have. So this is our last example. We're going to take a look at trying to find some segments and angles in this square. The only information that's given is the length from R to P. Our diagonal line is 24. Because it's a parallelogram, that means RP is being bisected, so I have 2 smaller segments that are each 12. Since the square is also a rectangle, my diagonal lines are the same length. Also, not drawn to scale, but my square is also a rhombus, which means I have 4 90-degree angles where point O is. So I'm actually dealing with 4 right triangles, and more specific, they're isosceles triangles. So I'm just going to go off to the side here. I have a right triangle. 2 of my sides are 12. I can use the Pythagorean theorem to try to find my missing length. And I'm just going to use, let's say we're using this triangle here. So I'm going to try to find what the length of RS is, and RS is my hypotenuse. So now the last thing I need to do is find the square root of my 288. And it's approximately 17. I'm just going to go out to the nearest hundredths, but my missing side is approximately 17 in length. So since it's a square, I'm just going to round that to the whole number 17. So my four sides should have a length of 17. Now the last thing I need to do is find missing angles. The four angles in the center would each be 90 degrees. Because I'm dealing with isosceles triangles, that means I have base angles that are the same. Each of those angles would be 45 degrees. I can get that because it's isosceles, or I can also get that from the fact that a square has a 90-degree angle at the corner, and being that the diagonal lines are angle bisectors, I would just take 90 degrees, cut it in half, and they're each 45. So in a square, that's unique to squares. You will always be dealing with four right triangles. They will be isosceles, and each of these smaller corner angles will always be 45 degrees in any square.